Hello, today we will discuss about Lagrange interpolations, another type of interpolation. In the last class we have discussed about interpolation and two different methods for interpolation, Newton's forward method and backward method. So today we will discuss about another method which is known as the Lagrange method. So the first, what is the idea about the interpolation? So if you have a set of value for independent variable x and its corresponding function value is given like this. So you have a certain values of x and its corresponding function values given over there. Okay, so you can draw the card if you have a less number of values, and you can have the idea about the card, the nature of the card. But if the number of particles is more, you really cannot draw this type of card, or you really cannot predict what is the nature of the function. So you need to use the concept of interpolation. If from a large set of values you need to find any unknown values which is not given. Say, so now you have a values of say x5, somewhere here you have x5, somewhere here you have x6. So if you have certain value within x5 and x6, say this is x5x, f5x dash. So what is the value of this function somewhere here? You really don't know. So by using the concept of interpolation, one can find this thing. Now here we're going to first try to write the Lagrange polynomial, and then we'll try to see how to solve this problem. Now the advantage of Lagrange method is that in case of Newton method, forward and backward method, the step size were equal. So the distance between x1 and x2, x2 and x3, x3 and x4 and others, they are of equal size. Step size was considered as h some constant. But if the values are not equal, say x1 and x2 and x2 and x3, the gap values are not equal. So then the Lagrange method will be used. If the independent variable are not equal spaced, then you can use the Lagrange method, the most important one. But if the step size is equal, then also you can use the Lagrange method. But this is the advantage of the Lagrange method over the Newtonian method. So first we'll try to draw the polynomial. First we'll try to write the function. So how to write this thing? So the function is given as, say, function is given as, say, some coefficient c1 f of x0. F of x0 means y0 plus c2 f of x1, or sometimes we can write this is as y1. Okay, so this can be written as y0. Okay, or function at x0. Same way, function at x1, this is given as y1. Say you can go up to certain n value, generalized value of this one. Now what is the idea about the coefficient, that c1, c2 or cn values? Okay, so you can write cn, yn, certain value. So what is cn? Now in a very generalized form, one can just think about this thing as x. X is the unknown value. So somewhere here you will try to find the function value. So you will be considering this is as some x. So the first we are writing it for x0. Okay, so here this will start from its next point. So we will go to left that particular part. So this will be written as x minus x1, x minus x2 up to x minus xn, the set of values. Okay, and here we will going to write the denominator part. We will going to write x0 minus x1. Okay, where we will going to find the coefficient x0 minus x1, x0 minus, sorry, this will be x2. Okay, this will be x0 minus x3 up to x0 minus xn. Obviously you cannot write it x0 minus x0, so whole term will be vanishing. So we will going to not write this one. So the coefficient for y1 can be written as x minus x0. Now obviously you cannot write x minus x1. Now this will be directly x minus x2, x minus x3 up to x minus xn. Now here in the denominator part, this will be x1 minus x0, x1 minus x2 up to x1 minus xn. And the generalized term is x minus x0, x minus x1 up to x minus xn minus 1. Obviously we are not considering the xnth term. Now here this is xn minus x0, xn minus x1 up to xn minus xn minus 1. Obviously xn minus xn cannot be considered. So this is c1, the coefficient, this is c2, this is c3, these are the coefficient values. If you know this one, you can write a generalized polynomial or generalized function, or if you want to, if you have your function, if you have your independent variable value, so you can get the function, but directly you can get the function value at that particular point. Now we will consider a numerical problem by which we can get the unknown function value. Now here we have a function or set of values where the x values independent variable and the function values are given 5, 6, 9 and 11. Just see they are equal spaced. If it is not equal spaced, then also you can use this thing. If it is equal spaced, you can use this. And the function values are also given over there. And you need to find the value for x is equal to 10. So x is equal to 10, this will be somewhere here. This value is not known. You need to find what is the value of function at x is equal to 10. So x0, so the first value is x0, 5, x1, x2 and x3. These values are given. Obviously this will be y0, y1, y2, y3. These are given over there. Okay. Now you have these values. Now we are going to put this thing in the polynomial. So how to write this polynomial? Now here we have this polynomial. So this is out of 1, 2, 3, 4 variables are there. So now we have the 4 coefficients C0, C1, C2, C3. Okay. So what is C0? This is x minus x1, x minus x2, x minus x3. Okay. So it starts from x0, x1, x2, x3. x0, x1, x2, x3. Okay. So now this is x0 minus x1, x0 minus x2, x0 minus x3 and the function at x0. Okay. What is C1? C1 x minus x0, x minus x2, x minus x3. Obviously x minus x1 is absent. This is x1 minus x0, x1 minus x2, x1 minus x3 and the function at y1 or function at x1. Now we can write it for x is equal to x2 and x is equal to x3. So C0, C1, C2, C3 we have your function. Now put the values. So you need to find your function at x is equal to 10. So you put this value is equal to 10. So x1, the x values are given 5, 6, 9, 11. Okay. So we're going to put x1. x1 is 6. You're going to put this one. x2 is 9. You can put this one. And x3 is 11. You can put this one. Okay. Now what is our x0 value? Okay. x0 value is 5. So what you have to do? x0 minus x1. So 5 minus 6. 5 minus 9 x2. And 5 minus 11. So you'll have the coefficient value over there. Multiplied with the function value. So function at x is equal to x0. This is 12. Same way we can get that one. So this is 10 minus 5, 10 minus 9, 10 minus 11 and this is x1 minus x0. So this is 6 minus 5, this is 6 minus 9, this is 6 minus 11. So you have the coefficient value and the corresponding function value is given as 13. So you can put this one. So you can calculate it for 4 different coefficients, C0, C1, C2 and for C3 with the function values. Now put these values, simplify this one and one can get what is the function value at x is equal to 10. This is a very simple method by which one can interpolate. A simple recapitulation. So the first and foremost thing, the Lagrange method will be applicable over the system, a set of values where the variables, independent variables are not equal space. Although we can use this thing, but the main use of the Lagrange method is for the not equal space set of values. Then you need to set that polynomial with the different coefficient and the function value multiplied with the function values. Then from the set of data, one can put this thing in the polynomial and one can find the desired function value at a particular point. Thank you.